Yeah, so this is the same loop we were talking about. You load a counter. Yeah. By the way, the counter doesn't have to be an internal register in the machine. The counter can be a memory location. So in the previous example, the counter was a register. It's a register B of the machine. But in this example, this example figure 3.2, the counter is a memory location. It's a memory location that you keep, you use as a counter. And of course, I tell you the situation where you need that. Sometimes you need a bigger counter, for example, that cannot be accommodated by register B. So you resort to a memory location. Sometimes you need both. In a specific problem, sometimes you need the memory location as well as a register. Yeah, there is a scenario which is called nested loops. I'm sure you must have heard about this even in Fortran programming or C++ programming. Your very early days of learning programming, they tell you something called nested loops. You know the do loop. What we're doing here is similar to a do loop, except that it's 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 not called a do loop, but it actually functions like a do loop. You see, so that's the thing. Here you have two loops. You have an internal loop inside an external loop. You see, that's the figure right here. Let me enlarge this little bit. Yeah. Here you load accumulator and store in port B. That's gonna be a the first counter. You load A, and we have two counters actually for this problem. We have counter 1 and counter 2. We load counter 1, put it in A, and load counter 2, and do the loop. You know, let me show you the inner loop. The inner loop is right here. Toggle the port. So, for example, you need to toggle the port. Toggle port B. Decrement counter 2. See, this is the inner loop here. See? This is the inner loop. So you keep decrementing the counter, and until that counter reaches 0, then you exit the inner loop. When you exit the inner loop, you go to the outer loop. So you start working with the outer loop. So you decrement counter 1, and you ask the same question again here. Is counter 1 0? Yes, that's the end. No, you go back and repeat the whole thing again. So you have a loop inside a loop. You have a loop inside a loop. Yes, that's the inner. Hi, Samson. How are you?
Hi, I'm doing great, Professor. How are you?
Good. Um, yeah, you can write on the outer too. You can do the same thing here. You can highlight the outer here. Yeah, this is the outer. Yeah, here you go. This is the inner and this is the outer. By the way, the loops are very important in something called time delay loops. Sometimes there is a famous problem where I ask you to create a time delay of, let's say, 100 milliseconds, or a time delay for 10 milliseconds. And you would use the loop concept to create the time delay. It's a lot of computation to do the time delay loops. You need to, for example, let me use this example for the time delay loop. Let's say, okay, we need to create a 10 millisecond delay. Then what are you going to do? How are you going to do it, the 10 millisecond delay? First of all, you need to know how many clock cycles that are needed to execute, to obtain a time delay loop. The clock of the microprocessor is 4 megahertz. That means each cycle of the clock is a quarter microsecond. Now, suppose you need a 10 millisecond delay, then a 10 millisecond delay divided by a quarter microsecond, right? 10 millisecond, that looks like 4,000. Yeah, I can do it. If you divide 10 millisecond by a quarter microsecond, that's like 4,000. So you need 4,000 instruction cycles. By the way, I placed on the web, on Beachboard, some material with the time delay, how to create a time delay. So you can read this information. It's under extra reading, I guess. It's under extra reading. There is a section, I called it manuals. I don't think that's it. I think it's under extra reading. Most probably it's under extra reading. So now, in the very particular example I was talking about right now, we need to create 4,000 cycles. If we go for 4,000 machine cycles or instruction cycles, if you multiply that by quarter microsecond, which is the inverse of the clock of the, then that's gonna give you 10 millisecond time delay. See? So the question is, how are you gonna write a program that consumes 4,000 machine cycles or 4,000 instruction cycles? You have to know how much each instruction takes. How many instruction cycles does each instruction take? Okay? And then you create loops. You create a loop like this, like the inner loop, for example. And you set some numbers and then find out how much time is the inner loop gonna take. How much time does the inner loop, how many instruction cycles to finish the inner loop, for example. All right. Suppose that the number of instruction cycles is 500. That's just a wild guess. Let's suppose we have 500 instruction cycles for the inner loop. We need an overall, let's say, 20,000 cycles for the whole thing. Now you divide the